Okay, I think we're recording. I'm going to run through some more of these notes on Fourier analysis. I've uploaded the PDFs for these course notes to the Blackboard website. The first one's called Fourier Stuff, Fourier Series of a Periodic Function.pdf, I think. So we'll go through that. I'm going to try to figure out a way to make this slightly more interactive. I'm probably going to ask you guys to have a class meeting with me in the near future where we sort of ping pong back and forth through some of this material. We're also going to do another set of notes, which is it's called Fourier Stuff, Calculating Fourier Series. And that includes a little sketch of some analysis for the wave equation that we were studying, the one-dimensional wave equation we were looking at before spring break. So we're going to take a look at these things, and at the end of this, or maybe in the sort of close to the end of this video, I'm going to talk about a homework assignment that I'd like you guys to work through. All right, so without further ado, I'm going to flip over to those notes. And I get to put my glasses back on. All right, Fourier series of a periodic function. So we talked about periodicity before spring break, right? We were thinking in terms of the time domain because we had been working with harmonic oscillators of various complexity. And we said, oh, a function is periodic if there's some quantity t that we can add to its independent variable such that we regain the original value f of t for all values of f of t, right? Okay, now sort of go back to what we were talking about recently. Think about how Taylor series work. Near some particular point in our domain, the function is equal to, assuming it's not a pathological function, assuming it's well-behaved, it's equal to the sum of an infinite number of terms where I just calculate this, and this becomes a constant, right? This is the nth derivative of the function of x evaluated at that x equals a value. So that's evaluated at some specific x. So that knocks x out of this term, right? And then the only place that x appears is in this power series expansion. Okay. If we have well-behaved functions of f of x, then we can take that f of x and expand it in these powers of x. And that seems counterproductive when you first learn about it. If I have some function like this, f of x is equal to sine of x, shouldn't I just use that? Because that's nice and tidy. So shouldn't I use that instead of saying, oh, f of x, which is sine of x, is also equal to x minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial minus what? X to the 7th divided by 7th factorial, and so on. Or if you just want to write an expression, it's this hairy thing, right? So I look at this, and it's a series, and series are hard. I look at sine of x, and I can just calculate sine of x, right? By either remembering the values for certain specific angles or just punching it into a calculator. So surely sine of x is simpler than that awful power series, this ugly mess on the right-hand side of that equation. That's only kind of true. It's more compact to write, but that doesn't mean it's simpler. Because think about how easy it is to integrate a term that looks like some constant times x to the n. So those rules are super easy to use, right? So sine of x, you remember how to integrate and divide, integrate and take the derivative of sine of x. But consider that we could write a function that is just as compact as sine of x, but is something really complicated and messy, right? Something that's absolutely hairy. And it would look very compact. But do you know how to integrate it or take the derivative of it? I wrote divide here because I'm an idiot. It's supposed to be derivative. But if we can take that complicated function, and I admit that sine of x is not that complicated, but it could be a more complicated function than sine of x. If we can take that thing and build a power series to understand it, then working with that power series is a cakewalk. All right, so previously, when we worked with power series, we were looking at Taylor series as a way to approximate. The lights always turn off around this time and then flick back on if the motion sensor picks me up. Okay, previously, we were looking at Taylor series as a way to approximate a potential energy function in the vicinity of a minimum. So if we had a complicated potential energy function, like the Leonard-Jones potential or something. It's a function of x, and it's a messy looking thing. But I could say, well, that's equal to some constant term, and that's meaningless because I can just choose my overall energy level and say I'm going to measure V is equal to 0 at this level or that level or that level. And it's only differences in potential energy that matter to me, right? So I just choose my level to be convenient. But V of x is equal to V naught plus V1 of x, and this has to be 0 if x is near the minimum or a minimum of V of x. So this V1x term will always be 0. We can calculate V1 using that Taylor expansion method, which is here, right? So I could calculate that V1, and it better come out to be 0. Otherwise, it'd have a constant force, right? Yeah, because you take the derivative of the potential to get the negative derivative of the potential to get the force, and therefore it wouldn't be a minimum. So this has to be 0 plus V2x squared, and this is the thing we wanted because we wanted this to say, look, this potential energy function that's complicated, near a minimum, it's parabolic. So it looks like a Hooke's law thing. So let's just steal results from Hooke's law. Okay, so let's catch our breath. When we were doing this, we were just getting a couple of terms, right? We were just taking the first few terms. We could calculate V3 for V3x cubed, but it was meaningless. We didn't stick it into anything because it's the anharmonic correction. We didn't need it. So we were doing Taylor series to get an approximation. Now, though, let's stick for the moment with the idea of an infinite series, right? So we're not just saying like, oh, I want to approximate something in one small vicinity, right? Okay, so this is a very awful hand-wavy argument I'm going to make to get at the underlying concept. Something you guys haven't probably done yet is make the transition to thinking of something like f of x as a vector. So we would agree, I think, having banged our heads on these kinds of problems for a while now, that you could write f of x as a naught plus a1x to the first power plus a2x to the second power plus a3x to the third power plus so on. And then maybe I should even write a naught x to the 0th power in here. We can think of this as breaking this vector f of x down in terms of a basis set, where the basis set is x to the 0th power, x to the first power, x squared, x cubed, and so on. Okay, so remember doing this kind of basic stuff? Got some vector A, and I just decide that there's an xy coordinate system, and we just draw it left, right, up, down because of our training, because we've seen it done that way 1,000 times. So we can then write this vector A as the sum of a sub x, the x component of A, times x hat, a basis vector that points in this direction and has a unit length, plus a sub y, y hat, same thing but in the y direction. So x hat is the x basis vector and y hat is a y basis vector. Okay, so when we just had vectors and we just thought about them as geometric objects, we were probably okay with the idea of an x and y basis vector. The process of finding those a sub x and a sub y terms, we could call that decomposing A onto its vector components, right? We'd be finding the coefficients for its basis vector, basis vectors. All right, this will not be proven here, but x to the 0th power, x to the first power, to the second power, third, fourth, and fifth power, and so on, form an orthogonal basis for real functions. So any well-behaved f of x can be represented in some neighborhood around some particular point as f of x is equal to a naught x to the 0th power plus a1 x to the first power plus a2 x to the second power plus all this higher order stuff, right? So we can think of this as being a basis vector that's like the unit vector x hat, except it's like a function or a number as well as that, right? This is like y hat, right? It's the next basis vector. This is like z hat, the next basis vector. And we're only used to thinking in terms of 3 spatial dimensions. So I don't have a letter that comes after z to say the x to the 3rd power polynomial there is like the basis vector. But I think you get the idea. There you go, the lights again. All right, hang on, I'll go pause the... do I need to even bother pausing it? I'll have to do too much stuff. I'm just going to go flick the lights on. I hate that. Okay, so if we had a couple of vectors to do operations with, we could break A down into its x and y components times those basis vectors. We could break a vector B down the same way and a vector C down the same way. And then if we wrote something like A vector plus B a vector is equal to C, also a vector, what that means is that A sub x plus B sub x is equal to C sub x. And A sub y plus B sub y is equal to C sub y. So I could say that the x and y components of the vectors A, B, and C are independent of each other. I don't use any of the quantity AY or any of the quantity BY to get CX when I'm calculating A plus B is equal to C, right? To get CX, I use AX and BX. I don't use any of AY or BY. So there's an independence between the X and Y components here. And this works the same way for our new basis set for f of x. So do you remember I grouped the coefficients of different powers of x together when we solved that very simple diffie-q, right? I said, oh, all the stuff times x to the 0th power is going to have to be identically equal to 0. All the stuff times x to the 1st power, all of it will have to add up to just be 0. All the stuff that multiplies x to the 2nd power, by itself, that coefficient will have to add up to be equal to 0, right? Okay, so keep that in mind. And now think, when we looked at this vector A, why do we have to choose x hat and y hat as the basis? I mean, is it because maps are laid out north, south, east, west? Or because of the metric system? And then I was just being stupid here. The Peace of Westphalia? Or because of the official rules to monopoly? We don't have to. That's the whole point. This x and y is just a mathematical abstraction. It's a it's a tool we're using to make some progress, right? So I don't have to use x hat and y hat, or if I wanted to use those letters, they sure don't have to point left and right just because we write left to right and up to down on paper. We don't have to use those. The vector can actually just live right here, and it's not embedded in a coordinate system at all. It's just a vector. What defines a vector? What is a vector? Well, the facetious sounding an annoying response to that is probably a vector is a thing that transforms like a vector. So really, these mathematical objects we're talking about, like this vector A, the way that they're best defined is in terms of their properties under certain transformations. So like a rotation transformation should change which way a vector points, but doesn't change its length. If I have two vectors and I rotate them, they should both kind of track with each other so that the angle between them doesn't change. So that's the kind of thing we would have to get to if we were doing more advanced mathematics. But my point here is this vector A does not have to live in that coordinate system. So let's choose coordinate systems to help us. We had this one, but let's choose a different basis set. Let's use, I call this I hat and j hat. And I chose a new basis vector so that I hat points parallel to A. That's really tidy and convenient for me because now A will have a component A sub I that's entirely equal to the magnitude of A. And that just makes my work easier because it's got no j hat component at all, right? The entire magnitude of this thing is parallel to I hat. So that helps me. Here's a question. Do these two things have to be perpendicular? Do they have to be orthogonal? And the answer is no, but it'll make your life so much easier that you rarely bother to set up non-orthogonal basis vectors here. Okay, why did I draw it like this? So my plus I was in this direction. Why did I draw plus j in that direction and not plus I and minus j? Why did I do that? You don't have to worry about this really, but we did this. We used this geometry and not this geometry because this is a properly formed right-hand coordinate system. So when you hear the phrase right hand, you think right-hand rule. And that right-hand rule is defined to work the way it does. You know, this is all connected, right? Like, so we live in right-handed coordinate systems. We could, since it's all just mathematical abstractions, all agree to work with left-handed coordinate systems instead. But we would have to change the way some things are defined. So what does it mean to be right-handed? All right. This is an XYZ coordinate system where Z is supposed to be coming out of the plane. And I know that it points out of the page and not into the page. I'm not looking down at it like this. I'm looking up at it like that. And I know that because x hat cross y hat has to give me z hat because of the right-hand rule. These three unit vectors are labeled sequentially. So if I cross them like this, x cross y cross z, or excuse me, x cross y is equal to z, this will give me a true statement, right? And that's, I don't know if you remember this, but that is true. Like we can prove this without worrying about the operating system stuff we're doing now for how coordinate systems actually work. We could prove it using the rules for doing cross products and everything. So if I build a three-dimensional coordinate system and I'm using some ordered triple of vectors like r, q, and s, I don't care which way they point, but let's just pretend they're all perpendicular and unit magnitude, nice and tidy, then I better draw my coordinate system so that r cross q is equal to s. This statement implies these next ones where I so-called permute these unit vectors in the correct order. So take this thing at the left-hand side and pop it off over to the right-hand side. That gets me q cross s is equal to r. Do it once more. Take this q, pop it off this side, bring it over here. I get s cross r is equal to q. Check this for me with x, y, and z, because I think I did this right, but I haven't thought, oh, well, it turns out I did it. So let's think about this. I was going to say I did this the other night when I was punch drunk, sleepy, but maybe I did it right. All right, so x, y, and z are in order. X cross y is equal to plus z. Is that true? X cross y plus z. Yeah. All right, let's pop the x off, bring it over to this side. Y cross z is equal to x. Is that true? Y cross z is plus x. Works. Z cross x is equal to y. I just pop the y over here, and then I'm left with z, x, y in that order. So z, x, y, let's see, z cross x, z cross x plus y. The whole thing works. So you can see this is a well-constructed right-hand coordinate system. Good, great. Everything works fine for me when I did this cyclic permutation. You can also set things up where you have the negative sign equation, and then you can do the cyclic permutations again, or you can switch the order of two things. So if this is my starting point, x cross y is equal to z, just switch the order of these two adjacent unit vectors, and it will give you the same thing, but with a minus sign multiplied by it. So there's some rules about how this stuff works. If you're interested, the Levi-Civita antisymmetric tensor is the thing you want to study. I know you won't do it, but listen, we are trying to scratch some kind of intellectual itch in you. Once in a blue moon, when I tell you about how something works and say, oh, you could go look this up, just do it once. Do it once for me this semester. Okay, so we called x, y, and z our unit vectors. They have length 1. The magnitude of them is equal to 1. Do they have to always be unit vectors for my basis set? And the answer is no, but it makes life easier. If you use orthogonal unit vectors for your basis, it's going to be a lot easier. I'm not going to prove it, but x to the 0th power, x to the 1st, x to the 2nd, x to the 3rd, etc., are going to be an orthogonal basis for us. I'm not going to prove what that even means because I haven't worked out what orthogonal means for these polynomials, for these power terms, right? So with vectors that I'm used to thinking of, I could say, oh, if a dot b is equal to 0, then a and b are perpendicular. They're orthogonal. What does it mean for a number to be orthogonal to another one? You have to figure out how to define an inner product for those things. And I'm not going to mess around with this. And the truth is I haven't thought about it in 20 years. So I can fake my way through it, but I'm just not going to bother proving the math stuff. We could make these things orthonormal over a certain domain if we put a coefficient in front of them and restricted the way we're doing the inner products and everything, but we're not going to worry about that at all. It's just not that important for what we're doing. So when something's not important, don't think about it rigorously. Okay, so you remember how we said, oh, so you start out with x and y, your original coordinate axes, but then you choose smarter ones, I and j. It's just a change of basis, right? We use different basis vectors. So what if we said that f of x is a vector, and it can be decomposed only in some regions as a power series in x? So we've decomposed that vector f of x on a basis of the powers of x. But now, here's the exciting part. You should be on the edge of your seats. Let's say that that vector is the same vector, but we're going to decompose it onto a power series in the sine and cosine functions. So f of x will be equal to g naught, some coefficient, times cosine 0th power of x plus h naught, just a coefficient, sine to the 0th power of x plus g1 cosine of the first power of x, h1 sine of the first power of x plus g2 to cosine squared of x plus h2 sine squared of x plus g3 cosine cubed, h3 sine cubed, and so on. So we're changing our basis for this function that lives in some independent variable x, and that could be x as a position, it could be x as time, because it's really going to be a t when we write this out. It could be anything. We haven't really specified much about this yet. And the restrictions on when we can do this, the so-called Dirichlet conditions, are very relaxed. Real functions that exist in the world that you mess with as a physicist, they will satisfy the requirements for this to work. We're just changing a basis from powers of x to powers of sine and cosine. This is a new power series in sine and cosine functions, right? And then, you know, if we were doing something like what we've done before, we'd say, oh, these terms will be useless to us for whatever reasons. The same way we got rid of that V naught term. This term would be useless to us for another reason. This term would be useful, whatever. We'd be doing something like that. We're not doing the same thing now. We're saying, like, let's think about what this thing looks like as an infinite power series in powers of sine and cosine of the original independent variable. Okay. We never write this that way. We don't write it as like cosine cubed. What we do instead is we fiddle. What the heck did I write here? We need the dimensions of, the dimensions of the arguments of the sines and cosines to be 1. So this is a mathematical function. We give mathematical functions, at this point in our careers, we give mathematical functions dimensionless quantities. So if x is a position variable, if it's like x is in your position on some x-axis, you better divide that by some characteristic length. It better be x divided by some L. Or alternatively, if it's a time, it better be t divided by tau, where tau is some time constant, to scale that thing appropriately so that you have a dimensionless quantity. And I've said this once or twice before. It's actually possible, using a power series expansion, to figure out what happens if you feed a mathematical function something that has units on it, but it's usually kind of nonsense and useless. Right? Think about the expansion of something like cosine and do that power series where you say, oh, what if I do cosine of time and I leave time with seconds in there? Well, 1 plus x squared over 2, so that's going to have units as seconds squared. 1 minus x squared over 2 plus x to the 4th over 4 factorial. Like, what do I have seconds to the 4th power? So it's going to be hard to think about what it means to have a sum where my units don't actually have the same dimension. I'll have to figure out some clever way to, when I'm done with it, wrap it all back up into another function to kind of hide that problem. All right, so we're not doing that. We're not worrying about stuff like that. We're just thinking right now, whatever I stick in here better be dimensionless. So we're not going to just send cosine and sine x a position or t a time. It's going to be something divided by something. All right. I think that's just me repeating this. Okay, the second thing, we're going to turn those powers of sines and cosines into sines and cosines to the first power, but with an integer multiplying the argument. So you've seen stuff like this. Sine to the second power of theta is 1 minus cosine 2 theta divided by 2. This is one you use enough that by the time you're like a second year in grad school, you'll know that one. It just shows up so much in your homework. Sine to the 5th power is equal to 10 sine theta minus 5 sine 3 theta plus sine 5 theta divided by 6. I don't remember that one. I can tell you that much. But the point is, there's a power reduction formula for, in general, sine to the nth power or cosine to the nth power that turns it back into a sine or cosine to the first power, but with a coefficient multiplying that independent variable. Okay, don't worry about it. We don't start with this formalism. So don't worry about getting to something that has cosines and sines that look like that. We don't do it when we're doing the calculation. Instead, we'll just have some rules for cooking up a recipe for what we're doing, which is a Fourier series. All right, so let's think about some f of x. we're going to say this f of x has a periodicity of 2 little l. I'm going to change my nomenclature later. So this little l is not the same as big L. It's what? Half of big L. But f of x plus 2l is equal to f of x. That's what it means. It's periodic, where 2l here is like the wavelength of this periodic function. You can put any x in here, and this remains true. That's what it means for this thing to be periodic. If that is the case, then that function f of x can be given as this power series that's been turned into a sum of cosines with that number n and sines with that number n multiplied by the argument pi x over L, pi x over L. A naught, it's a constant. An and bn are also constants because the x stuff gets integrated out of them. Do I have the thing I need on the next term? Yeah, okay, so I'm not going to scroll back. We have a cookbook to find those an and bn, and we can prove that this is what those things look like, but we're just going to accept it, all right? So a naught's 1 over 2l, and then the integral from minus L to L, f of x dx. How do I figure out where to start? Where's minus L to L? How do I choose the wavelength? This is set up to assume that the thing is, it actually doesn't matter. As long as 2L is equal to the periodicity of the function, then this is arbitrary. You could integrate it over any chunk of the periodic wave function. It wouldn't matter. This is the kind of thing we could actually do if we were in front of a chalkboard and I can explain what I'm getting at. But I'm going to change my nomenclature, so don't worry about it too much. All right, so they're just these cookbooks. The first term is just the thing integrated over its wavelength. The second thing, the a sub n's, is that function, whatever it is, multiplied by cosine n pi x over L, and then I integrate that thing over the wavelength. And I do that for n equals 1, n equals 2, n equals 3. I do the same thing to get the bn coefficients, right? Okay, so remember what these are. They are coefficients in a power series expansion in powers of sine and cosine. And there is a reason related to odd and even functions why I have both sine and cosine basis terms here. If I had just an even function I was analyzing, if my periodic function f of x were just even, I could get away with just doing the cosine parts. If my function f of x were just an odd function, I could get away with just doing the sine parts. The a sub n's would all be by default 0. And in the other case, the b sub n's would all by default be 0. But because most functions are not purely odd or purely even, but the sum of an odd part plus an even part, all functions have to be that. I will need both sine and cosine for a general periodic function. Okay, and remember these a sub n's and b sub n's, I've integrated all the x dependence out of that. Okay, that's exactly like what we're doing when we found power series in x. So if I had f of x near some point I was analyzing, notice incidentally, I'm not bothering with that anymore. I didn't say this had to be near some point. The Dirichlet conditions that make it possible for this thing to work are very generous, and I don't have to restrict my attention to x near some point. But let's go back to the power series. For f of x near some, in the vicinity of some a, it's equal to f of x at that point plus that first derivative divided by 1 factorial. And there is no x dependence in that. The x turns up only here. And then the next term, second derivative of f of x, evaluated x is equal to a. That evaluation knocks off the x's. There's no x in this thing anymore. The x behavior shows up just here, which is good because it means it's just a power series. So we're doing the same thing here. This is integrated over x, which means the x's go away. This is integrated over x, so x's go away. Integrated over x, x's go away. Okay, that is the first chunk of notes I want to talk about. So let me stop sharing that, and I'm going to pause this for 2 seconds while I collect the other notes. Okay, I had to run around and do a couple things related to 406, the advanced lab. But we are going to move on with another set of notes that's going to take what we just did and slightly change the nomenclature that we're going to use for doing Fourier series. The derivations I'd worked through to get a rough idea of how this connects between power series and power series in the trig functions. I admit to having been a little, not sloppy, but having followed a convention that made it simple to do some stuff that would form a coherent argument. So when I did that, I ended up with an expression for the Fourier series where the argument was what? N pi x over L, little l. And that is not my preferred formalism. I like a factor of 2 to show up in there because those 2 pi terms crop up in tons of stuff we do with wave motion, right? So 2 pi times something is usually how I move between angular and regular frequencies and other measurements like that. So I'm going to change our nomenclature over just to get the factor of 2 where I want it. And if you're trying to understand how this works, if I remember correctly, the difference is that we previously were running over a periodicity of lowercase l over 2 to lowercase l over 2, negative l over 2 to positive l over 2. And now we're going to do 0 to l. So we're going to change the way we're writing periodicity. And when we do that, that will give us the form for our Fourier series that looks most natural to somebody who's studying wave motion. So that's why we're bothering to do that. Don't be frustrated because I haven't made you calculate anything with the previous expression yet. So when I change a bunch of factors of 2, you're not allowed to get mad at it yet. Then we're going to talk about this thing with the wave equation. So you may barely recall before spring break, we used a very, very shaky model of a wave on a string, a propagating wave on a string, to build a differential equation, a partial differential equation for studying waves more generally. Our derivation of that was very shaky because of some preposterous assumptions that went into it. But it turns out that that's actually the wave equation for studying wave-like phenomena. And where our derivation failed is not because we have an imperfect model for wave-like phenomena, but because a real string has some elasticity, but it can't push. And so we don't have this nice real Hooke's law force in it, coupling adjacent elements in the system. All right, let's actually get to the notes. Okay, Fourier stuff, calculating Fourier series. So we previously introduced the idea that we could take any well-behaved function, f of x, which is to say any function that obeys the Dirichlet conditions. And you don't need to worry about what they are because the functions we're going to be studying are based on real phenomena. So I don't have to worry about whether or not they have a finite number of removable discontinuities or whatever the requirements are, because a string does not have discontinuities. That's going to be a good argument for any kind of cop-out excuse we need to have to not worry too much about the Dirichlet conditions. The upshot is most of the phenomena we would ever study in physics will obey the requirements for doing Fourier analysis. All right, so any well-behaved function f of x can be represented as the sum of sine and cosine functions. And here's that form we were looking at previously. So what I was throwing a little fit about is I have this n pi x over L, and I really want 2 n pi x. I'm desperate to get that 2 pi together. Okay, and I think the reason that derivation ends up with n pi instead of 2n or 2 pi n is because it was set up for some engineering analysis, and I think people there just didn't care about having a really tidy formalism that would more seamlessly connect to other stuff, like in our case, analysis of motion of waves. All right, so we're gonna fiddle with this to get that 2 pi n. We're gonna have a periodic function. We're gonna assume that the function is periodic going back to negative infinity and positive infinity. Is that realistic? No, but don't worry about it. We have a periodic function and it has a periodicity big L. So I'm drawing that differently, right? This was lowercase l, and we were doing minus L over 2 to L over 2 or something like that. Or no, we were doing 2L. I've said it wrong. We were doing 2 times lowercase l is the periodicity, I think. Forget that. Our periodicity is now big L, right? And in the future, if we start thinking about the periodicity of a thing that has a wavelength, that's going to be L is equal to lambda, right? And that will let us build a Fourier series to represent the behavior of some function as a position of x, where x is a spatial coordinate. That would be a spatial Fourier series. We could also think about periodicity for functions that oscillate periodically in time and have a period capital T. And in that case, that quantity L would be something like L is equal to T. And if that's the case, we're going to be calculating a Fourier time series, right? So when you see this analysis where I'm saying, oh, consider some function of x, that doesn't mean that x is a position. It just means it's a variable. It could be anything I want to study. I can take a Fourier analysis of I can make a Fourier series for a periodic function that is periodic in whatever variable I'm interested in, right? But we're mostly going to work with spatial variables and time variables. But when you see x, don't think, I can never put in t's. This could be f of t and t. All right. If that's unclear, come harass me about it over Zoom or something by email. Okay, so f of x, which is periodic in x with periodicity big L, can be written this way. F of x is equal to a naught over 2, and notice there's a factor of 2 here, plus the sum from n equals 1 to infinity, a sub n cosine 2 pi nx over big L, plus bn sine 2 pi nx over big L. And there are those 2 pi's I want, right? I was desperate to get the 2 pi's in there. Okay, and by putting my a naught over 2, I was able to simplify my rules for generating the a sub n's and b sub n's. This a sub n works for a sub 0 as well, and it didn't do that previously. This is it, 2 over big L, x naught to x naught plus L, f of x cosine 2 pi nx divided by L dx. Notice that x has units of whatever, L has the same units, so those cancel. N is a number, so it has no dimension. It's just 1, 2 pi, just a number. So this cosine has a dimensionless argument. This has a dimension, but that's okay because it's going to be the dimension of this term. This has a dimension when it's integrated, but it'll cancel with that. So the a sub n's should have the same dimension, same units as f of x. Same thing holds true for the b sub n's. Okay, things to consider. Once again, we are integrating out the x dependence. This thing is integrated over dx. So all this x stuff will go away. What do I choose x naught to be? Anything you want. The function's periodic, so choose x naught to be right here. All right, well then you just go like from here to here. That's one period, right? Or here to here, that's one period. Choose something else. Choose x naught to be here. We'll integrate from here to there. Any x naught you like, integrated from that x naught to x naught plus L. So those integral bounds, once you pick wherever x naught is, you know where you're going. You're going to x naught plus L. But x naught is arbitrary. It does not matter. We mentioned this 1 over 2 times a naught term. Compared this to the other cookbook we had for generating ANs and BNs. We had a separate rule for a naught there. Here, by putting a factor of 2 in the Fourier series, we get rid of that separate rule. This can now be used for a sub zeros. Okay, what else do we have to do? All right, let's take a look at this again. F of x can be represented, it's some complicated function, but it can be represented as a sum of a constant term, right? We integrated out the x dependence in here. So a constant term plus then some coefficient times cosine 2 pi times 1 times x divided by L plus another coefficient, cosine 2 pi times 2 times x over L plus another coefficient, cosine 2 pi times 3 times x divided by L, and so on. And then the same thing with the bn and the sine 2n pi x over L term. All right, so this is a constant with respect to x. This is a constant with respect to x. This is a constant with respect to x. The x's have all been integrated out. So the f of x dependence on x shows up entirely in this cosine set of terms and this set of sine terms. The a's and b's are just coefficients. numbers. And maybe it's a number, maybe it's got a variable in there. Like maybe there is a lambda and a q and an r, whatever. There can be things like that in there, but they're not functions of x. Just like when we did power series in powers of x, right? We would take those derivatives, substitute in x is equal to a, divided by a factorial. That coefficient then was just some constant. And this is just me repeating exactly that. Okay, now I'm going to say, let's take a look at these other pages to look at the solution here. All right, so I'm going to say, let's see if this sine of 2 pi x minus vt divided by lambda is a solution to the wave equation. So we're going to walk through what it means to verify that this function is a solution to the wave equation. And then I'm going to ask you to do something that will take these terms and see if they are also solutions to the wave equation, which is going to be the reason we're bothering to do this, right? I'll walk through the overview of this again soon. So let's do this. Let's take a look at this function I picked up arbitrarily. And now I'm going to examine to see if it's a solution of the wave equation. Remember that the way we get the solution of the wave equation at some time t is we take whatever the initial function is, so say it's sine 2 pi x divided by lambda, and we just substitute in x minus vt. And that takes our initial condition, sine 2 pi x over lambda, and propagates it forward to time t. Okay, so let's check out that quick note. Recall the one-dimensional wave equation. It looks like this. We derived this when we were looking at a string perturbed from its equilibrium position. So y there was a physical distance away from its equilibrium value. So as we went along the axis of the string, we took a second derivative with respect to position along that axis. Then we also took a second derivative with respect to how the thing's changing in time. And we realized that those two quantities are connected by this 1 over v squared term. I have it here from before spring break. I didn't lose my notes this time. This is like actually 1 year, the anniversary of last week, I think it was, of me getting exposed to mercury in an accidental spill, which I did not commit. But a bunch of my, well, first of all, I had to go stand in the safety shower and scrub off with a dish soap for, oh my God, hang on. Okay. I was complaining about how this time a year ago, there was a mercury spill that I stumbled into, discovered, not a big one, and I was contaminated. So my microphone is freaking out. I had to go stand in the safety shower for a while, scrub off with dish soap because it's a really good degreasing agent. It's really good at lifting something like mercury off your skin. It could get in your hair, right? And then it hangs on to you. So I had to get that off. And then I drove home in a bunny suit, a hazardous waste suit. And a bunch of my stuff was contaminated by mercury. So it was collected by the hazardous spill response team that manages this kind of stuff. And they stuck it in a 40-gallon drum, but along with other stuff that was contaminated with the mercury, and sent it to a landfill in Tennessee where it's buried and its GPS coordinates are cataloged. So all my notes from the last time I taught 211 are at some specific geological coordinates. At some point, we should ask health and safety to tell me what those coordinates are. It'd be fun to look them up on Google Maps and say, oh, they're on the satellite. That's where they buried my laptop case and all my notes. Okay, we have a one-dimensional wave equation. It was a very shaky derivation for a string because we're relying on the physics of strings. It's a correct equation for phenomena that travel as waves. This sort of defines what it means to travel as a wave. Put aside strings for a minute and just think about, oh, an electromagnetic wave or an acoustic wave or something like that, a pressure wave. Anyway, what if we guess that y is equal to y naught, some amplitude, times the sine of 2 pi x minus vt divided by lambda is a solution to this problem? All right, so I took the first derivative, dy by dx, and I got this, 2 pi over lambda, y naught, cosine 2 pi x minus vt divided by lambda. And then I took the second derivative, and I got minus 2 pi over lambda squared, y naught, sine 2 pi x minus vt all over lambda. So that's this term, the spatial second derivative. All right, then I did the same thing for dy dt. I got the first derivative with respect to t minus 2 pi over lambda v. So there's a v here that didn't show up in the other first derivative. V, y naught cosine 2 pi x minus vt over lambda. I do the same thing again. I take the derivative with respect to t, and I get minus quantity 2 pi v over lambda quantity squared, y naught sine 2 pi x minus vt all over lambda. That goes into the time derivative side of things, right? So this is telling me the curvature as I move left or right from some point is what will determine how that point changes subsequently in time. Or you can read it right to left and say how that thing is changing in time will determine the curvature of the medium, the disturbance in the medium around that point. Does this work as a solution to our 1D wave equation? We just plug in. So d squared y by dx squared, here we go. 1 over v squared, here we go. D squared y by dt squared, here we go. So this thing had a v squared term. You can see it there. That's not on the left-hand side, but it cancels with my 1 over v squared. Okay, and that leaves me with a is equal to a. So both sides work, right? All right, so what I've found is this particular function, y is equal to y naught sine 2 pi quantity x minus vt, quantity divided by lambda, is a solution to the one-dimensional wave equation. All right, so that was our digression. Here's a problem for homework. Show that a naught over 2, which is the first term in our Fourier series, is a valid solution for the one-dimensional wave equation. Don't write down a naught as an integral equation. A naught is a constant, right? So you could write down the integral equation for solving for a naught and then try to take those derivatives, and that stings. Don't do that. Just say a naught, a constant, plug it into those derivatives. So show that that satisfies the 1D wave equation. Then show that all the other a sub n cosine 2 pi nx over lambda. Sorry, that should be a lambda, not a big L. It could be a big L. It doesn't make any difference. I just did it previously with a lambda, and I like the way that I like, but whatever. We already said that for spatial Fourier transforms, big L is equal to lambda. Show that this thing and this thing for arbitrary n are also solutions of the one-dimensional wave equation. And again, a sub n and b sub n are constants now. You've already integrated this stuff and just gotten a number. So it's very easy to take derivatives of constants, right? Don't sweat that stuff. Okay, so show this thing as a solution, and it's a subset of showing this set of functions as a solution and this set of functions as a solution. Don't do it one by one. Don't say like, first I will do it for a1 cosine 2 pi times 1 times x divided by lambda, and check that. Now I will do a2 cosine 2 pi 2x divided by lambda, and do that. Just leave it as an n, right? Because you can do that. You can take derivatives with n's in there. That'll work fine. All right. What we are doing is making an argument that an arbitrarily complicated waveform, whatever complicated shape is propagating along this wave, can be broken down into the sum of simple sine and cosine waves. And we know that how those sine and cosine waves behave on strings or electromagnetic fields or a medium like air that supports acoustic waves. We know how those well-behaved disturbances propagate. We can build rules for the well-behaved, easy to describe analytical solutions for the well-behaved phenomena. Then we'll show that whatever arbitrary shape we bang into that medium initially, that shape will propagate and obey all the nice rules we get for sine and cosine waves because it's built out of sine and cosine waves. Is that clear? I hope. Think back 1,000 years ago to when we were talking about driven damped harmonic oscillators. And I said, let's just assume that the driving force is some F naught times sine times some omega, we don't know what it is, sine omega t. And I said, is that accurate? And then I went to the back of the classroom and I poked that mass on a spring. And I said, look, this is not sinusoidal. It's me periodically tapping. That's not sinusoidal at all. But I explained that force, that driving force, which looked like nothing, 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 up, nothing, 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 up, nothing, 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 up. I explained how that periodic force could be represented as mostly, that's kind of like this. That's a pretty good approximation. And then I said, yeah, to be accurate, we have to add in some fast stuff too, some other sines and cosines, but we're not going to worry about that because there's going to be one term that's bigger than the others in this periodic function. So we're just going to pretend that this periodic function is periodic and looks like a sine. And I made the argument that it's not, but that's not something we're really going to worry about too much. And I think I made just a qualitative argument at the time. I remember it was at the far right-hand side of the board. I drew a diagram showing something like that, where my periodic but non-sinusoidal driving function, I pretended that it looked like a periodic sine function. And then I said, and you'll add in these smaller functions as well that are also periodic sines and cosines. That's what we're doing right now. We're taking some function. It is not a sine or cosine, but we're saying we can build it out of sines and cosines. And then we have rules for how sine and cosine waves will propagate. We know that they satisfy the differential equation for a one-dimensional wave. So if we know that that's true for the sines and cosines, it's going to be true for the arbitrarily complicated waveforms we start out with. All right, this has gone on long enough. I'm going to upload it. Hope you guys are all doing well. I'll send out an email to tell you to take a look at this and start working on this homework problem. It is Thursday at 11:13 p.m. and the date is March 26th. Why don't you work this solution out, take a photo of it, and email it to me for Thursday of next week? Does that work for you guys? I can hear no one saying no, so we're going to say it does. All right, talk to you guys soon. Hope you're all holding up okay.